Earth is the third planet from the Sun, and the standard against which every other rocky world is measured. So central is it to our reckoning that the very units of astronomy are drawn from its motion, the day from one turn on its axis, the year from one circuit of the Sun, and the astronomical unit, the base yardstick of the solar system, from the average radius of its orbit. It travels that orbit at nearly 30 kilometers a second, along an ellipse so gentle that its distance from the Sun varies by only a few % across the year. It turns once on its axis, against the background stars, in about 23 hours and 56 minutes, a little short of the 24-hour solar day, because in one rotation it has also crept along its orbit and must turn a fraction further to face the Sun again. And its axis is tilted some 23.5 degrees from the vertical, the simple fact that gives us the seasons, and that a single large moon has helped to hold steady over the ages. Measured as a planet, Earth is the largest and densest of the 4 rocky worlds. It is not a perfect sphere but very slightly flattened at the poles by its own spin, some 21 kilometers wider across the equator than from pole to pole, and it is denser than any other planet in the solar system, denser even than Venus, a clue that it hides a large, heavy core of iron. That clue can be made precise. From the way Earth's mass resists being spun, a quantity astronomers can measure from its motion, we can tell that its material is not spread evenly, but concentrated strongly toward the center, the unmistakable signature of a dense metallic heart. This chapter treats our home not as a familiar landscape, but as a planet, to be weighed and compared, and it does so through the 4 great coupled systems that make Earth distinctive: its layered living interior, the magnetic field that shields it, the ocean and atmosphere that clothe it, and the moving plates that uniquely recycle its surface. Earth is some 4.5 billion years old, an age read from the radioactive clocks in the oldest meteorites and moon rocks. It grew from the disk of gas and dust that circled the newborn Sun by a process of accretion. Dust stuck into pebbles, pebbles collided into boulders, and then into mountain-sized bodies, and these swept up their neighbors into ever larger worlds until over tens of millions of years a planet had formed. The violence of those impacts, together with the heat of radioactive decay, melted the young Earth into at least one deep ocean of molten rock. And in that molten state the planet sorted itself by weight, exactly as oil and water separate. Dense, heavy iron sank through the melt to gather at the center and form the core, while the lighter rock floated above to become the mantle, and the lightest materials of all rose to the top to make the first thin crust. This sorting by density, driven by gravity alone, is why Earth today is built of concentric shells rather than a uniform ball. The most dramatic event of Earth's youth was the birth of the Moon. The leading account holds that near the end of Earth's assembly, a body about the size of Mars, given the name Theia, struck the young planet a colossal, glancing blow. The impact flung a vast cloud of vaporized and molten rock, torn mostly from the outer layers of both worlds, into orbit, and from that ring the Moon swiftly gathered itself together, while Theia's iron core sank and merged into Earth's own. This single idea explains a whole cluster of otherwise puzzling facts: why the Moon is so much less dense than Earth and has only a tiny iron core, for it was made chiefly of rock; why the Earth-Moon system spins with so much angular momentum, and why the rocks of the 2 bodies share an almost identical chemical fingerprint, for they were made from the same shattered material. And the large Moon that resulted has since served as a gravitational anchor, steadying Earth's tilt, and so keeping its climate more even than it would otherwise have been. Below a few kilometers, no drill has ever reached Earth's interior. Almost everything we know of it we have learned by listening to earthquakes. When a great quake ruptures, it sends 2 kinds of wave through the planet, and their behavior betrays the structure they pass through. Primary waves are compressions like sound and travel through solid and liquid alike. Secondary waves are shearing, side-to-side motions, and a liquid, having no rigidity to shear, stops them dead. And here lies the crucial clue: beyond a certain angle from any earthquake, the shearing waves simply vanish, casting a shadow right across the far side of the planet. That shadow is the fingerprint of a liquid layer deep within the molten outer core. Sharp changes in the speed of the waves at particular depths mark the boundaries between the layers, and from millions of such readings, gathered over more than a century, seismologists have assembled a detailed reference map of Earth's insides. The depth of each shell, its density, and the pressure that reigns there. The picture that emerges is of 4 great concentric shells. Beneath the thin crust, a few kilometers of it under the oceans, some tens of kilometers under the continents, lies the mantle, a shell of solid rock reaching almost halfway to the center, to a depth of nearly 2,900 kilometers. Though solid, the mantle is hot enough to creep and flow over the ages like an immensely stiff fluid, churning slowly as it carries heat outward. Below it begins the core, first the liquid outer core of molten iron and then, at the very heart, a solid inner core of iron about the size of the moon. That the inner core is solid while the layer around it is liquid seems a paradox, since it is the hotter of the two. Its center is as hot as the surface of the sun, perhaps 6,000 Kelvin. The resolution is pressure. At the center, the crushing weight of the entire planet squeezes the iron so hard that it freezes solid despite the heat. And that inner core is slowly growing, freezing outward, as the Earth gradually cools. All of this makes Earth a living planet, in the geological sense, a body with an internal fire that has never gone out. The heat welling up from the interior to the surface amounts to some 47 trillion watts, and it flows from two sources in roughly equal measure. Part is primordial, the original heat of formation, left over from accretion and from the sinking of the core, still leaking away 4.5 billion years later. And part is fresh, generated continuously by the decay of radioactive elements, uranium, thorium and a heavy form of potassium, sprinkled through the rock. It is this internal heat, escaping through the slow churning of the mantle, that drives everything restless about our planet. The drifting of the continents, the eruption of volcanoes, the raising of mountains, and the making of the magnetic field. A small planet like Mars cools quickly and its fires die. Earth, larger, has kept its heat, and with it its geological life. Among the products of that internal heat is one of Earth's most vital possessions, a global magnetic field, of a kind that among the rocky planets only Mercury now shares, and that Venus and Mars entirely lack. At the surface it behaves, to a first approximation, like the field of a great bar magnet buried at the center and tilted about 11 degrees from the spin axis, the field that turns every compass needle toward the poles. But it is no permanent magnet, for the interior is far too hot to hold any fixed magnetism. Instead, the field is generated anew continuously by what is called the geodynamo. In the liquid iron of the outer core, heat and buoyancy drive vast convecting flows, and the spin of the planet, through the Coriolis, force twists those flows into an organized helical churn. Iron conducts electricity, a moving conductor generates electric currents, and those currents, sweeping through the core, sustain the very magnetic field that shapes them, a self-renewing engine of electricity and motion, deep beneath our feet. This deep engine is anything but steady. The field drifts and changes from year to year, and far more dramatically, from time to time it reverses outright, the north and south magnetic poles trading places. We know this because the record is written in stone. As molten lava cools, it freezes into itself the direction of the magnetic field then prevailing, and layer upon layer of ancient rock preserves a long history of the flips. They come at no fixed rhythm, sometimes within 100,000 years of one another, sometimes not for tens of millions, and the last full reversal took place around 780,000 years ago. A reversal is not the work of a moment. Over several thousand years, the field first weakens and grows tangled and complex before reforming in the opposite sense. Earth's field has weakened somewhat over the past 2 centuries, and it is natural to wonder whether another reversal is approaching. But the honest answer is that we cannot yet predict such things, and it remains an open question rather than a forecast. Reaching far out into space, the magnetic field does more than guide compasses. It carves a vast protective cavity around the planet, called the magnetosphere. Streaming out from the sun in every direction is the solar wind, a thin gale of electrically charged particles moving at some 400 kilometers a second, and carrying the sun's own magnetism with it. Charged particles cannot easily cross magnetic field lines, so where the solar wind meets Earth's field the two come to a standoff, and the field holds the wind at bay. The shape that results is not a sphere but something like a windsock, squashed on the sunward side, where the wind presses the field inward to a distance of about 10 Earth radii, and drawn out on the night side into an enormous tail streaming for hundreds of radii downwind. Ahead of it all, where the supersonic wind is forced suddenly to swerve aside, stands a bow shock, like the wave thrown up before the bow of a ship. Within this cavity, the field traps its own population of charged particles, holding them in 2 great donut-shaped zones, the Van Allen belts, discovered by the very first American satellite in 1958. Other particles funnel down the field lines toward the magnetic poles and plunging into the upper air set it aglow. These are the auroras, the shimmering curtains of the polar skies. But the magnetosphere is more than a light show, it is the planet's shield. By turning aside the solar wind, it prevents that wind from stripping the atmosphere away into space, the very fate that appears to have befallen Mars, which, lacking a global field, lay open to the erosion of the sun. When the sun is stormy, gusts in, the solar wind buffet the magnetosphere, the belts swell, the auroras blaze and descend to lower latitudes, and electric currents surge that can disrupt power grids and satellites, the space weather that a technological civilization has learned at some cost to watch. At the surface, Earth possesses a machine found on no other known world, plate tectonics. Its rigid outer shell, the crust together with the cool, stiff rock just beneath, together about 100 kilometers thick, is not a single unbroken skin, but a mosaic of a dozen or so great plates and many smaller ones, all in slow motion, sliding over the hotter, softer rock below. The idea grew from an old and once ridiculed observation that the continents look as though they were torn apart and could be fitted back together, which Alfred Wegener framed as continental drift early in the 20th century. The missing mechanism was found only in the 1960s, with the discovery that the floor of the ocean itself is spreading, being created, along great undersea ridges and carried outward like a conveyor belt. The engine that drives it all is the internal heat, escaping through the churning mantle, which hauls the plates across the face of the globe at about the speed a fingernail grows. The plates meet along boundaries of three kinds, and each writes its own signature on the planet. Where plates pull apart, along the mid-ocean ridges, molten rock wells up to form new sea floor, and as that fresh rock cools, it records the direction of the magnetic field, so that the field's reversals are stamped into the sea floor as a pattern of parallel stripes, running symmetrically away from the ridge on either side. Those magnetic stripes were the clinching proof that the sea floor spreads, and they serve as a precise clock for the motion of the plates. Where plates collide, the denser one bends and plunges back down into the mantle, carrying old crust with it and throwing up the deepest ocean trenches, arcs of volcanoes and the greatest earthquakes. And where plates merely grind past one another, as along California's San Andreas Fault, the strain builds and releases in quakes. When all this machinery first began is still debated, perhaps 3.5 billion years ago, perhaps earlier, for the very recycling that defines it erases its own oldest record. The deepest importance of plate tectonics, though, is not geological but climatic. By dragging carbon-bearing rock down into the mantle and returning carbon dioxide to the air through volcanoes, while the weathering of rock on the continents draws that same gas back down and buries it, the moving plates close a great planetary cycle, and that cycle acts as a thermostat. When the world warms, weathering speeds up and pulls carbon dioxide from the air, cooling it. When the world cools, weathering slows, volcanic gas builds up, and it warms again. This slow, self-correcting feedback has held Earth's surface within the narrow range where water stays liquid for billions of years, and it has done so even though the sun itself has grown some 30% brighter over that time. It is this thermostat, more than anything else, that many scientists regard as the key to Earth's long habitability, and its absence on Venus and on Mars is the leading explanation for why those worlds, which may once have been temperate, are temperate no longer. Earth's atmosphere is a thin veil beside the crushing envelope of Venus, yet it is the medium of all weather, climate and life. It is made overwhelmingly of two gases, nitrogen at 78% and oxygen at 21%, with argon and a small but consequential trace of carbon dioxide making up most of the rest. That abundance of free oxygen is, on the scale of planets, extraordinary and profoundly unnatural. Oxygen is so reactive that, left alone, it would within a geological instant vanish into rusted rock and oxidized gas. That it persists in such quantity means it is being continuously replenished, and the only agent that can do so is life, through photosynthesis. Earth's oxygen-rich air is, in other words, the most conspicuous mark that our planet is inhabited, the very kind of chemical signature that astronomers now hope to detect in the atmospheres of distant worlds as a possible sign of life. The air is layered not by what it is made of, but by how its temperature changes with height. In the lowest layer, the troposphere, where all our weather lives, the temperature falls steadily as one climbs, for the air is warmed from below by the sunlit surface. Above it in the stratosphere, the trend reverses and the air grows warmer with height, because there a layer of ozone absorbs the sun's ultraviolet rays, the same ozone layer that shields all surface life from that harmful radiation. The atmosphere is also in ceaseless motion. because the sun heats the equator far more strongly than the poles, and because the planet's spin deflects every moving current of air, the atmosphere organizes itself into great wheeling cells and swift high-altitude jet streams that carry heat away from the tropics toward the poles. This circulation sets the pattern of the world's winds, its deserts and its rain belts, the machinery of climate, driven by sunlight and steered by the turning of the Earth. Yet Earth's true defining feature is its water. The ocean covers some 70% of the globe to an average depth of nearly 4 kilometers, and it is the planet's great thermal flywheel. Water stores and releases heat so reluctantly that the ocean smooths out the swings of temperature and, of late, has soaked up the overwhelming share of the extra heat trapped near the surface. Ocean and air together form a single coupled fluid, circulating heat around the world. What sets the temperature of the whole system is its balance of energy with the sun. At Earth's distance, the sunlight delivers about 1,360 watts on every square meter it faces, spread over the whole turning globe, and after nearly a third is reflected straight back to space by cloud and ice, the planet absorbs something like 240 watts on every square meter. Balance that incoming warmth against the heat the Earth radiates away, and one can calculate the temperature the surface ought to have. That calculation gives a chilling answer. A bare Earth balancing sunlight against its own radiated heat should sit at about 255 Kelvin, some 18 degrees below freezing, a frozen world. Yet the true average surface temperature is about 15 degrees above freezing, fully 33 Kelvin warmer. The difference is the natural greenhouse effect. Certain gases in the air, chiefly water vapor and carbon dioxide, are nearly transparent to the visible sunlight streaming in, but they absorb the invisible infrared heat. The surface tries to radiate back out and trap it near the ground, so the surface must warm above that frozen figure until it can force enough heat past the blanket to balance the books. It is the very same physics that has made an inferno of Venus. The difference is only one of degree, of how much of these gases each atmosphere holds. On Earth the effect is gentle and life-giving, and it is the strength of the feedbacks that amplify or damp it, the response of water vapor and of clouds and of ice, that remains the central question in understanding how our climate answers to change. Earth's deepest scientific value in the end is as a standard of comparison, the one rocky planet whose interior, magnetism, air, ocean and moving crust we can study in exhaustive detail, and against which every other such world must be read. The sharpest comparison is with its two nearest siblings. Venus, Earth and Mars began as broadly similar worlds, built of much the same material, and each, it seems, may once have held liquid water, Venus with early oceans, Mars with its ancient riverbeds and lake floors written plainly across its surface. Yet the three diverged utterly. Venus into a scorched, crushing greenhouse, Mars into a frozen and airless desert, and Earth alone holding its water and its temperate climate across 4 billion years. Why three sibling planets formed side by side should have come to such different ends is the central question of comparative planetology. And the same question, writ large, that we now ask of the rocky worlds being discovered around other stars. Three coupled things, all met in this chapter, seem to explain Earth's persistence and its siblings' failure. The first is the thermostat. Earth's moving plates drive the slow carbon cycle that has buffered its temperature for eons, a safeguard Venus and Mars both lack. The second is the magnetic shield. Earth's dynamo turns aside the solar wind, whereas little Mars, cooling fast, lost its internal heat and its magnetic field early, and then watched its atmosphere stripped slowly away by the unshielded sun, a loss now being measured directly by spacecraft in orbit there. And the third is simply size and heat. A planet's mass governs how long it can hold the internal fire that powers convection, tectonics, and the dynamo. Small, Mars ran down and died. Venus, near Earth's size, kept its heat but vented it through a rigid, unmoving lid rather than through drifting plates. And only Earth struck the fortunate combination of ample mass, mobile plates, and a protecting field. And so the lesson Earth teaches, studied as a planet, is a subtle one. Habitability is not a simple matter of a world's distance from its star, of sitting in some comfortable zone where water could exist. It depends on the whole coupled, evolving interplay of a planet's interior and its surface, its atmosphere and its magnetic field, unfolding together over billions of years. A world may lie at just the right distance, and still, like Venus or Mars, lose everything that made it hospitable. It is precisely this framework, interior, surface, air and field, understood as one connected system, that astronomers now carry outward to interpret the thousands of rocky planets being found around other suns, worlds we may never visit and can know only by the faint light of their atmospheres. Earth, the one living planet we can examine from within, is the key by which we hope to read all the rest, the Rosetta Stone of the search for another living world.